The overload checker is a first feasibility test for the feasibility of verifying the feasibility of a disjunctive constraint. The intuition is the following. So you have on this example 3 activities A, C, and B. And as you can see, that's the time window, okay, for the 3 activities. So if you take the union of the time window, this is what you get. At the earliest, you can start from there, that's defined by A, and at the latest, you should finish at that time, that's defined by B, right? That's the latest one. So you know that you have only this very large time window, okay, for all the 3 activities. And if you put the duration one by one next to each other for the 3 activities, starting from the start time of the time window there, you see that you exceed the interval that was defined by the dashed line, right? So it means that it's clearly infeasible to schedule the 3 activities given these time windows, right? We would overload, what we say, we would overload the resource. So let's rephrase this, what we have just seen previously using formula. What we have seen is that we have found a subset of activities omega composed of A, B, and C, such that the earliest start time of the omega, that's here, plus the sum of the processing time, take the summation of all the duration, right? You exceed the latest completion time of omega that was defined by this one, right? If you detect a subset of activities omega with this property, you can clearly backtrack because the resource is infeasible. You would overload the resource. You can convince yourself that this formula is exact, is also working, right? If you apply it. So you've got 0, that's the earliest start time, plus the sum of the processing time, you will end up with 16, and that's larger than 15, which was here exactly the latest completion time of this set omega. And so we should backtrack. What's the time complexity to verify this formula for all the subsets omega? Well, you need first to enumerate all the subsets, so that's 2 to the power of the number of activities on your resource. And that's not very practical, as we can imagine, to embed an exponential time algorithm just to verify one propagator. So we need to find something else. And this something else will be to improve a little bit the filtering rule by introducing a new definition, that is the left cut of an activity. So we define the left cut of the activity J here as all the sets of activities that have latest completion time less than or equal to the latest completion time of the activity J. So what it gives for the activity A, okay, you take the latest completion time of A, that's this one. All the one that finished before, well, there is this one and this one, because that's less than this and this is less than this. So what you have is that you have, of course, A itself, because that's a less or equal, but you also have the activity C and you have the activity D. Okay, what about for that one? You take again the latest completion time there, and the one that is before is, of course, C itself, but you also have the activity D, right? Because this was before this. What about the latest completion time of B? It's here, and clearly all the activities have a latest completion time less than or equal to the one of B, which means they are all part of the left cut of the activity B. That's for the left cut. Once we have defined the left cuts with this formula, we can rephrase the overload checker rule, right? That was the initial overload checker rule. It can be reformulated as for all activity J, if the earliest completion time of the left cut is larger than the latest completion time of the last cut, then we should fail, right? That's clearly equivalent to this. And the left cut of a set is the latest completion time of the left cut is by definition of the left cut itself, the latest completion time of J itself, because they are all less or equal to the latest completion time of the activity J by definition, right? So we can rephrase the overload checking rule as this rule. And what is nice to see there is that now we only have to verify it for all J in T, and this is less than for all subsets of activity in T. So we can already see that here we gain a lot because we are moving from an exponential number of checks to a linear number of checks. And the earliest completion time of a set of activity, we already know how to compute it efficiently with the theta trees. So overall, the time complexity for this is n times order of n log n. Okay, n is for this. And to compute the earliest completion time of the left cut, that's n log n. We can do that with the theta tree, for instance. And you can convince yourself that on this example, we have what we expected. So the earliest completion time of the left cut of B is 16, right? And 16 is larger than 15, which is the latest completion time of B. And this is why we should also fail by applying this rule on this example. So that's exactly the same as what we did before. If you write down the pseudocode for the algorithm using this filtering rule, this overload checking rule, this is what we have. So we have for all the activities J, we initialize the theta tree, okay? The initialization of the theta tree is only to compute the earliest completion time of the left cut. And then we will introduce all the activities that belong to the left cut of J. Okay, that's log n for each insertion. So n log n for all the insertions. And then we verify, okay, in constant time, because we just query the root node of the theta tree. We verify if it is larger than the latest completion time of J. We just fail, and we fail by throwing an inconsistency exception, right? So again, n log n for the initialization. We have n times log n time complexity for each insertion, okay? And since we have an external loop here with n iterations, the total time complexity will be n squared log n. We can improve this time complexity because so far we didn't took any advantage of the fact that we have an incremental insertion, right? Except that we pay log n for each insertion, but we could do much better by iterating in a little bit in a smart way over these activities instead of this arbitrary 1 to n order, right? The thing is, what we can see here is that if we sort the activities according to the latest completion time, we can see that the left cuts will be nested, right? The left cut of if we sort them like this, you see that the left cut of the activity 3 is a superset of the left cut of the activity 1, because we just have added the activity 3, and so on. Okay, so if we sort the activities according to the latest completion time, we have the nested relations for the left cuts. And we can take advantage of that to define a new pseudocode for the overload checker rule. So we initialize now the theta tree externally to the loop, and we will sort the activities according to the latest completion time, so that the left cuts of the activities according to that order, the ones once they have been sorted, they are nested, right? So you iterate over the activities in the nested order, and now you just have to insert the activity in the theta tree, and it will contain the earliest completion time of all the subset of activities that belong to the left cut of J. And so you just have to verify that the earliest completion time of the theta tree, if it is larger than the latest completion time of the activity J, you throw the inconsistency exception. So let's wrap up the time complexity. Just the initialization of the theta tree is n log n, because you will sort the activity according to the earliest start time. Then you pay n log n for the sorting of the activities. You iterate, each insertion there is log n. So overall, this loop here is again n log n. And so the total time complexity is order of n log n, which is better than the previous n squared log n. Okay, so it's better than the n squared log n because now we are working with nested sets, and it was not the case before. Let's see what it gives on this example. you initialize, you sort the activities according to the latest completion time, right? That gives the order C, A, B, right? So the first one that finishes is C, then it is A, then it is B. You sort them, so that's C, A, B. You initialize the theta tree, but initially the theta tree is empty, which means that we have set the earliest completion time of all our activities in the theta trees to -infinity. By the way, that's an interesting example because, as you can see, in the case the number of activities is not a power of 2. You just have here, it is as if you have a node that contains nothing, right? And this is the way it works with theta trees, for which the last layer is not a power of 2. So initially the theta tree is empty, so you have a processing time of 0 and earliest completion time -infinity everywhere. Okay, and so obviously the earliest completion time at the root node is also -infinity, and the sum of processing time is 0. Then we will iterate. We go inside the for loop, and we will iterate first on C, then A, then B. And for each of them, we will insert them in the theta tree. So let's start with the insertion of C. You update everything there, starting from the leaf node corresponding to the activity C up to the root node. You update everything according to the formula that we have seen for the theta trees. We do know the verification that the earliest completion time, which means 9, is not larger than the latest completion time of the activity J. Activity J is activity C, so it means the check will be, is 9 larger than 13? That's the check. Okay, it's not the case, so we should not detect any failure at this point. The next activity that we will insert in this order is activity A, okay, but because that's the second one that finishes at the latest. We insert the activity A, we update everything up to the root node to reflect the fact that it is now inserted inside the set of the theta tree. And we do the verification, and now the check is 11, so the earliest completion time of A and C is 11, larger than 14, and 14 corresponds to this one, so 14, that's the latest completion time of A. It's not the case, so we should not detect an inconsistency at this point neither. And finally, we insert the activity B. The activity B, we update everything starting from the activity B, okay? That's the node of the activity B. We update everything. Now we've got 16 for the earliest completion time for the set A, B, and C, because at the third iteration, we have inserted all the 3 activities. And the test is now 16 larger than 15. That's the case, right? And we will throw the inconsistency to reflect that it's infeasible to schedule all the 3 activities A, B, and C inside the current time windows.